Ask a climber at the Red River Gorge what kind of rock they are climbing, and they will likely know it's sandstone or even that it's Corbin sandstone.
This is quiz. Corbin sandstone?
Corbin sandstone.
Corbin sandstone.
In fact, you could probably pull up to anyone's house in the area and they'll know it's sandstone.
How are you?
Good. What kind of rock do we climb on at the Red River Gorge?
Limestone? Corbin sandstone. Sweet, sweet Corbin sandstone.
That's right, sweet, sweet Corbin sandstone. But what about Corbin sandstone makes it so great to climb? Where do these big juggy pockets come from? What is it that makes this particular area so conducive to the formation of perfect climber holds? Geologists from the University of Kentucky gave a couple tours to answer these questions. Here is a snapshot of some of the information. Over 300 million years ago, in the Carboniferous period, the continent of Africa crashed into North America, leaving Beteville just a 7-hour car drive from Gambia on Africa's east coast. The collision between the continents created the Appalachian Mountains. At the time, the Appalachians were as high as the Himalaya. This collision is not what formed the Red River Gorge, though. The Red is not a mountain range or the foothills of the Appalachians. Neither is it a canyon carved out by the Red River or the remnant of ancient glaciers. The Red River Gorge was once a river delta. When the Red was in its infancy, a climber visiting the area would find herself standing at a river delta west of the Appalachians. Rivers in the Appalachian Range were bringing sand and sediment down into a large valley adjacent to the shallow sea which ultimately formed the Cumberland Plateau. Jason Dortch and Steve Martin are geologists from the University of Kentucky. They will explain why the Gunks and the Red were formed both from rivers depositing material from the Appalachians, but ended up with different rock, conglomerate versus sandstone.
And this was a river system. Okay.
This whole thing was a river system at some point. Okay.
Entire gorge, the Gunks, all of it.
Okay.
It's eroding material off the ancient Appalachian Mountains
Right.
that were way higher than they are now.
Yeah. Okay.
River depositional features. See these depositional features such as like different types of bedding and like ripples and things like that you can still see in the sands and like how they were deposited. If you go up to New York, if you go to the Gunks, right, it's closer to the mountains, right? So it's steeper, it's higher energy, and that's why they're coarser grain. We'd call that a conglomerate, right? So they're a bunch of pebbles stuck together. So there's climbing style differences that you see, right? Also deposited by river systems, the Gunks. So the only difference is grain size.
Oh, wow.
Same process.
Where we climb, the rock is a layer of Corbin sandstone over shell, siltstone, and a thin layer of coal. Parallel stress joints formed in the Cumberland Plateau, and this provided pathways for water to flow or seep into the ground. The water physically and chemically weakened part of the rock mass. The sandstone nature of the rock is important in the formation of our cliffs because sandstone erodes mechanically, whereas limestone cliffs form mostly by dissolution, which is a chemical weathering process. Over time, the rock broke away, the gaps continued to widen, and we had our ridges and cliffs. The amphitheaters form for the same reason that arches form. The curved shape enables tensile stress to be converted into compression, which supports the rock above in a shape that is like a third of an arch. Once the roof is too overhung, think horizontal beam, or intersect with a joint fracture, it breaks away into rockfall.
So Kentucky has the most natural arches of the eastern states because of mostly this sandstone right here. Cross-bedded, jointed sandstone. And I'll tell you about joints in a minute. We're right here, okay? The second most concentration of natural arches in the country. First would be Moab, okay?
Yeah.
And most of the natural arches you can see in the state here occur along this the eastern boundary of the eastern Kentucky coal fields. The reason here being this sandstone is kind of bottom of the section. Stratigraphically, the sandstones are thicker. Okay, so you get these nice cliffs and you get various holes in the rocks. All right. So And so the rocks have moved around a lot, okay? And the stress is built up into the rock. Another type of fracture in the rock, which is important for natural arches, are these cracks right here, okay?
Oh, really?
These are joints, and joints relieve stress, okay? Water flows through those joints, okay? It gets to a certain point where it just can't go any further, it's got to go somewhere. And so the water does a lot of work in the natural arches, in creating natural arches.
The UK Geologists led a tour to the venue in the Cave Fork Recreational Preserve. Climbers all over the world come to the Red for its big overhanging amphitheaters.
This example here indicates a joint control to me. And so you can see a couple of joint lines here. There's a large boulder kind of lower here, and then there's that face. And that joint crack runs along effectively the face. If you imagine that joint line continuing along the face of this rock, there may be more rock on this side. That rock is falling away, right? Because there's sort of a break there, and it's a natural weakness. That joint is followed all along the plane of this rock behind us. And you can actually see it all the way on the other side by that sort of orange strip there by that platform, because that joint is followed. And we think that the joint is probably what controls this exact shape here.
That's what Jason said.
Yeah. Jason would know about the joints more than I will, but...
And so as these rocks they're deposited as sediment, you bury them. And the process that goes from sediment to rock is called diagenesis, okay, where it turns into a hard rock with pressure and depth. There are fluids in between the grains. That's what makes it a sedimentary rock, because it's made of grains that are cemented together. And so as this is going through diagenesis, and maybe after, you have fluids flowing through the rock, okay? And it's depositing iron deposits. These are iron-rich fluids flowing through the fractures. And that's what's causing the weathering you see on these rocks. It's the weathering of the iron.
If you go to a beach, you have like sand, and then you'll see like a very fine grain like layer of black minerals probably around, right? And if you go with a magnet, you can pick up a bunch of those. It's probably like magnetite or illite, some other magnetic iron-bearing mineral. Quartz sand, like these small quartz grains, are like so dense, so they'll be like bigger, and then the little iron grains will be smaller because weight versus surface area, what can be carried by that water system. It'll be a bigger piece of quartz and a smaller piece of metal, right? And they're heavier and they're denser, so they tend to end up on the tops or the bottoms of each like sand deposit, right? And so you can kind of view these packages, right? These resistant kind of iron layers that are sticking out as outlining beds of sand.
Yeah.
Right? So this would be the bottom and the top of this bed.
This explains the thin iron rails on walls like Newcomb Tower, but the Red is known for having big juggy pockets. The jugs and pockets that we climb are formed due to uneven weathering of the exposed rock. Our sandstone at the Red is special because it contains iron oxide, which forms a hard, dark crust or patina over softer rock. This creates durable, unique holds on otherwise steep overhangs.
Whoa.
So a lot of these features you see called Liesegang Banding.
Liesegang bands, or patterns or rings, are the hard iron circles and swirls that the Red River Gorge climber will easily recognize. Some look like iron pipes buried in the rock, laid there just to give a climber a great handhold. But these are not man-made pipes. Liesegang patterns are named after Raphael Liesegang, who was a German chemist and photographer born in Germany in 1869. His research into photographic emulsions led to his discovery of Liesegang rings. Liesegang holds are formed when iron and manganese in pore fluids precipitate near or on a cliff surface.
Okay.
Since the Liesegang bands formed at the Earth's surface, they are much more chemically stable and thus hold the sand grains together very tightly, forming pockets, jugs, and chicken heads. So, here's a summary of why the Red River Gorge is climbing heaven. 1. Our distance from the original source of our sedimentary rock and the energy of the rivers bringing the depositional material. 2. The water that seeped into our sandstone was rich in iron and manganese. 3. Our sandstone was created from river deposition rather than wind or aeolian deposition. The sandstone in Moab was formed from very fine wind-blown sands, silt, and dust. This is why Moab has very straight splitter cracks, but none of the reds, pockets, or jugs. 4. Our plateau was stressed. These stress fractures turned into joints that eventually became the multitude of ridges and amphitheaters we see today. A climber's heaven. After Raphael Liesegang, rock, chemically stable and thus hold the grain